now let us look at that parametric model from the spectral domain or the frequency domain. So, what we get here, that from the equation of the air model and that the error term, that with the help of which we are actually extracting the parameters. The first one is the synthesis model, that if we drive it by a white noise and we know the air parameters, how we can get a signal like y n. The next one is the analysis model, that where we are trying to extract the model parameter, because we do not know the driving sequence, and the coefficient, that is Ak's. So, given the signal y, we are trying to do the linear prediction, given the fact that for the time being we have assumed that we know that model order, and one way to make that we have taken a sufficiently large model order. So, we can compute that prediction y tilde n, and we can compute that prediction error. So, if we take the z transform in both the case of the equations we get, one is for y z in terms of h z and x z, another is for the error term E, we get E z in terms of A z and Y z, we get they have some relationship, because H z can be represented as that G by A z. So, these two filters, that H z and A z, they are inversely proportional to each other and they have a relationship in that way. Now, if we take y n, we have actually captured that signal, that output. If we treat that as a deterministic signal, because we have just one set in hand, even if it is a stochastic signal or a stochastic process, we do not have multiple that the sets of y n. So, we can treat that as a deterministic signal, and using the Parseval's theorem, what we can get, the total square error, it should be same in the time domain as well as the frequency domain. So, we can write eta, that energy of the error in the time domain, that is same as the energy of the signal in the frequency domain, and from there E z or E omega, to be more precise in this case, where z is taken a point on the unit circle. So, we can represent that in terms of A and y. So, it can be represented E z square, or the spectrum of the error, in terms of the square of that polynomial or filter A omega, and the autocorrelation of the output S y, or spectrum of the output, to be more precise. So, it is a convolution of that. On the other hand, what we get, we can do some mathematical manipulation as E z equal to A z into y z. Now, we can replace the value of y z, we know that the value is h z into x z, and h z can be represented as g by a z. So, we get from the right hand side that a z will cancel, because it is appearing both in numerator and denominator. So, we are left with g into x z. So, the prediction error is a scaled version of that input signal. Now, in this previous analysis, what we have seen that x n is either the driving force, it is either a impulse function or direct delta function or a white noise, and for that x omega is constant. Hence, as the E omega is also a scaled version of x omega, it will also have the same characteristics, that means it should be constant over any frequency. So, in other words, what we can tell, the error is also white, and for that reason that the filter is that what we are determining here using the autocorrelation method or autocovariance method, we call it as a whitening filter, because the output or the prediction error what we get, that gives us a white spectrum, okay, or white noise. Okay. That is why it is called that whitening filter. Here some more observation. As the model order increases, the total squared error, that is eta p, it actually decreases, eta p tends to 0. So, what we can conclude from there, a multiple things we can get. The first thing, for a model order P, if we look at this model, we are making use of P plus 1 autocorrelation values to compute the model. So, the model impulse response has actually same ACF as that of first P plus 1 ACF of the signal, and as the P increases, which means the model ACF becomes more and more equal to the signal ACF. First we are matching with P plus 1 ACF starting from 0, and as the order is increasing, the ACF of the filter impulse response and that of signal, that is actually we are finding a match, we are making use of them. So, in that way, increasing the model order, we are getting the same value for the filter ACF as well as for our that model ACF. Now, ACF and PSD, they are just Fourier transform pairs. So, they are, if we can catch one, we get other also. So, as the P increases and it tends to infinity, what we can tell, the model ACF, it becomes identical to that of the signal ACF, and model PSD would be identical with the signal PSD. The simple reason is we are making use of more and more lags of ACF with the increase in the model order. So, we get a identical matching between them. So, in other words, we can infer that given any spectra, we can actually approximate by an all pole model of an appropriate model order. That means, if we do not restrict that model order, any model order is fine, then given any spectra we can actually model by all pole model. Previously we have told in case of biomedical signal AR model is good, but there may be case that where the MA model would have been more appropriate. We may not have encountered such situation, that is why we do not know, or ARMA model should be a better model in terms of a compact representation, but we started with an AR model because of our lack of knowledge. So, what would be the situation in that case? That is an important question, because what we have told that parametric model is very powerful so long the assumptions are correct. If the assumptions are wrong, it can actually lead us to very dangerous situation. So, we are bound to check that what is the penalty we can have to pay by taking only the AR model in case of a more general model like ARMA model. So, what we see that if we are ready to increase that model order and give a flexibility in that, given any signal, or to be more precise any signal spectra, we can represent it by the AR model of a sufficiently large model order. Okay. So, that is the importance of this derivation. So, now we come to another important question, that how do we select the model order. Okay. Given the AR model performs better and better, where do we stop? We can put it also in that way, because we know as we keep on increasing the model order, say using the Levinson-Darwin algorithm or any other technique, we see the error becomes less, and in that case where we can tell that the right time to stop to avoid overfitting. The first thing to note here, lower the model order leads to a smoother PSD. We get a smooth PSD, but if it is not again appropriate, then by over smoothing we may lose some actually prominent peaks. Now, if we keep on increasing the model order, what will happen? We would get number of actually spurious peaks, which will be more specific to that actually that ensemble. That means, we have taken a set or a vector y n or a set of values of y n. If we take another set of observations of the same stochastic process, we will find the spectrum will change. Those peaks will change their location, that is why we call them as spurious peaks. Okay. So, increasing the model order, what it is doing? It is trying to do overfitting in that signal, though it is reducing the error and matching more and more to that given signal. It is not actually giving us more new information about the underlying process, rather it is suffering from overfitting. So, we need to find out a way. The first observation what we get, that as we increase that model order, there will always be a decrease in error, or error will remain same. So, we can say error is actually a non-decreasing function, or rather non-increasing function of the model order. Either it will decrease or it will remain constant. So, based on that fact, all the model order selection techniques have been proposed. The first one is very simple, it is based on that fact that it will remain same or it will reduce with the increase of the model order, the prediction error. So, the plan 1 is, let us take the ratio of the error for order p plus 1 divided by the previous actually error for model order p, and this ratio is expected to be less than 1 or very close to 1. So, we take the difference from 1. Now, when this value, this ratio comes to very close to 1, determined by a threshold, small threshold delta, when it is coming closer than that, then we should stop. So, that is the first simple technique. The next one is using again the final prediction error. The plan 2, it suggests that we should take again the prediction error and we take a multiplier along with that. So, if we look at this term n plus p by n minus p, we get the numerator is monotonically increasing or linearly increasing, the denominator is again linearly decreasing, and initially as the n is very large, the change will not be prominent, but as the p is growing, it will become more and more prominent, and two together it will give a nonlinear increase. On the other hand, the prediction error, that is rho hat p for the model order p, what we get if we draw the curve that with respect to p, that the prediction error is actually decreasing in this way. This is the prediction order rho hat p, and the first term it is increasing in this way. So, the minimum will come at certain point. In other words, actually what we are doing here, we know the final prediction error, it will decrease very slowly, and to come to a constant value it may take very large model order. It can keep on actually reducing in very small way, and in that case to find out that threshold delta is a difficult choice, because that depends on the signal and that depends on the process in hand. So, what we should do, we need to add some penalty for the increase of the model order. So, for that we have taken the correction term here, which is increasing with that model order, so that as the p is increasing, that penalty is also increasing, and we stop at some point when the two curves they cross each other or restrict from the overfitting. So, both these techniques are actually empirical techniques, and they have actually less theoretical background. So, there has been a proposition based on the information theory proposed by Akaike. So, it is known as Akaike information criteria, which has given a technique to select the Akaike information way, that it depends on again the prediction error power, we take the log of that and multiply with n. So, this term that will go, that will actually decrease with the model order, and the second term will linearly increase. In fact, for the theoretical derivation, Akaike has found that this term should be p, but when people tried to use that, they found that if we use a scaled version of it, that is, if we use 2p, we get more accurate values. So, that is what is used in practice. So, in this case, what we will get, that again the curves would be like this with the increase in the model order, that the first term will decrease, that is n log of rho p. The other one is 2p is increasing linearly. So, we will get the point where the minimum we will get where the two intersect with each other. So, that will give us the optimal model order. Okay. So, that is about the model order selection. So, we can use any of these technique, and out of them the last one is the theoretically more sound and more accurate one, though it is a bit more complex. So, here first we see some example that what is the difference we get when we take the FFT and directly FFT, that is periodogram technique, or if we go for that AR model to compute the spectra. At the top, here we are showing the signal at hand, that is an EEG of channel O1. The corresponding that FFT spectrum or periodogram based spectrum is given here, and we know that the periodogram, it gives us a more clean view than the autocorrelation function to check that where the signal energy is more concentrated. That SCF also has same amount of information, but the representation is not so clear or direct. Now, let us look at if we compute the same using the AR coefficient, what we get. Using the model order 6, here we have taken the AR model, we get a very clean peak very near to 10 hertz. That means, alpha components are there, we get it very clearly, and it is much more prominent than what we could get in the periodogram. Okay? We can check that. In the previous that FFT based spectrum, if we compute, here also we are getting that more accumulation at this place, but the peak is not clear. There are multiple peaks, that makes it difficult to find out that where is the location of the peak and to decide on it, whereas the AR model makes it very clear. Now, if we increase that model order, instead of taking the model order as 6, if we go for model order 10, what we get, this peak that is near 10, that remains there, it is not disturbed, but it is a bit accentuated, it is becoming little more sharp. At the same time, in the valley region, that is this part, Earlier there was a very subdued one single peak here. Now, instead of that we are getting two peaks. In the valley region we are getting actually, rather than peaks we can say more undulations we are getting. So, that is the difference it creates if we use the increased model order. So, the change is not much. So, penalty is not that big in terms of the spectra, but certainly it will increase the computation. So, we always prefer to use that optimal model order, which will give us the smooth spectra, and we can reduce the unnecessary computation which does not add any value for the signal analysis. Okay. So, this is about, we get that idea that how the model order selection affects, and we get the first hand also the idea that how the spectrum computed by the parametric model is superior than the PSD technique, given that we have taken as a appropriate model order. If by mistake we have just stopped at 2, then the situation could have been different. Okay? It would not, it may not resemble actually the signal spectra. So, now we will look at one more thing that we have seen for the speech signal. The septal coefficients are very good as features. So, here we see the relationship between the AR model and the spectral coefficient, because with the SEF we could get some relation with the spectral coefficient. We expect the AR model also may have some relationship, or the expectation can be increased, like the autocorrelation helped us to, autocorrelation of the signal helped us to get the septal coefficient. Same way, can the AR coefficient help us to compute the septal coefficient, because it is helping us to compute the spectrum of the signal. Okay. So, from that what we do, first we take that all pole model Hz, where the poles are located in the unit circle, and using the Lorentz series we can actually represent it as a power series, and if we take log in both the side, which is one of the things that is required for the septal coefficient, or to go to the septal domain we need to take the log. So, if we take that, we get in the right hand side some H hat n, okay, as the coefficients of the different order of z to the power minus n. Now, using the definition of the complex spectrum as the inverse Z transform of the log of Z transform of the signal. So, what we need to do? We need to take actually inverse Z transform of the log of Hz. So, we get the series H at n as the septal coefficient of the signal H n. Okay. So, we could get actually septal coefficient in this way, and let us see that if we take the AR model represented by the model coefficients A k's for k equal to 1 to p, what is the relationship between them? So, for that we replace Hz in the left hand side, that log of Hz we have taken, we replace Hz by 1 by Az, and after that we can differentiate both the side by z to the power minus 1, because the polynomials are, we are getting their power of z to the power minus 1. Okay. Please keep in mind, it is not with respect to z, but z to the power minus 1, because that helps us to do the computation. So, left hand side what we get, the log of x is 1 by x, and then we get x to the power minus 1. So, we will get x to the power minus 2. So, by cancelling that power we get it, that using the chain rule we get the derivative in this form. Okay. We get here below a z, and we get that after taking the partial derivative, this is the term we get. In the right hand side we get n times h at n as the coefficients of z to the power minus n plus 1, or we can write it in this way, z to the power minus within bracket n minus 1. Okay. And to make it actually simple, to simplify it, we can multiply both the side with the denominator of the left hand side. So, we get both the side polynomials, and in the left hand side we get the power of z starting from z to the power 0 to z to the power 1 minus p, that is the power of z in the left hand side. Right hand side, however, it could be infinite, but because both the sides it need to match with each other. So, the coefficients has to match. Coefficients of z or z to the power minus 1 need to match in both the sides. So, using that property, what we can write, that h at 1 equal to minus a 1 and h at n for n equal to 1 to greater than 1 to p, that means starting from 2 to p, we get it is minus a n minus some more term. So, as we compute h 1, using that we can compute that h 1 hat, with that value we can compute h hat 2, and using h hat 1 and h hat 2 we can compute h hat 3. So, in that way we can go up to the pth coefficient. So, that the p spectral coefficients we can compute in that way. Okay. And according to the AR model, the model order is p here in this case. So, those many septal coefficients are only important, and we can compute them using the AR coefficients. So, if we have the AR coefficients, we did not have to do the Z transform, Fourier transform, taking the so many things, taking log, taking care of the that phase unwrapping. We can directly use the AR coefficients and get the septal coefficients from them. So, that is another important result we could get by learning the AR coefficient. Thank you.